Today I want to talk about a software algorithm that's used absolutely everywhere. Of course, it's in your laptop and your PC and your smartphone, your tablet, but it's probably also in your smart central heating unit. It's in a smart speaker. It's probably in your smart television. Probably even makes its way into some vending machines. So it's a group of algorithms called hash functions. I want to tell you why they're useful and how they work. So if you want to find out more, please let me explain. Okay then, let's get into this. So, what are hash functions? Put simply, a hash function is a mathematical algorithm that takes an input of any size. So that means it could literally be a string or a whole file. So as I say, such as a string, and converts it into a fixed length output value called a hash. So you might put in 3 megabytes and you still get out 5 or 6 bytes. You might put in just the words hello world and you still get out 5 or 6 bytes. Now these are useful in two distinct areas: in hash tables, which is about data structures and how you store things in the memory of a computer so you can access them quickly, and in cryptography. So I mentioned hash tables there. So a hash table, also called a hash map, is a data structure that stores a key, which is the hash, and then a value, that's the string that you want to store, that is good for fast lookups, fast insertion, and fast deletions, usually on an average of 01 time. If you don't know what 01 time means, I do have a video about how you understand those notations here on this channel. Now, a hash function maps the data to a specific location in a hash table, enabling fast storage and retrieval of that information. So you want to put something like, a name and address into a hash table. You use the hash function, you get this kind of unique key that's 5 or 6 bytes long, whatever, could be even longer, and then you're able to put the data in that part of the table. Of course, sometimes the table is very small. You might just get a number between 1 and 100. Anyway, the point is, I'm going to talk loads more about hash tables in another video. This is really the starting video to talk about the hash functions, so that we can use the hash functions in a hash table. So that's where we're going to be looking at those in a future video. Now, this is a programming tutorial, so we're going to start with some C programs, and I'm going to show you the simplest hash for an integer. Now, it's really as simple. This is the simplest possible hash for an integer. It uses the modulo operator to fold a potentially large integer into the range of the table. So if your table's only got 100 entries, but of course an integer can be a huge number, a couple of million or something. So you want to say, where am I going to put it in those 100 spaces? So example, I've got a table size of 100 and I've got 1, 2, 3, 4, 5. I use modular, and that tells me it should go into slot 45. So a hash table needs an array index, not an arbitrary big number. So it needs the 45, not the 1, 2, 3, 4, 5. And then taking the remainder after division means that we kind of make sure it fits into this. That's what the modulo does. Clock arithmetic, some people call it. And here is that very function. So it's hash for an integer. You pass in the integer, you tell it the size of a table, and it just does the modulo on it. Really, really simple. So again, if you want to store 1, 2, 3, 4, 5, and you've only got 100 slots, you do the modulo and you get slot 45. Now, of course, other numbers are going to hit slot 45 as well. And that's when we're going to talk about hash tables, what do you do when there's collisions and things. But this is the simplest idea to show you how it works. Okay, so let me introduce you to my hashing examples program. The code will be up on GitHub. Basically, it's a program that I've written that goes through all these different hashes. So let's try with the first one, as we've just looked at. If you do the hash integer of 1, 2, 3, 4, 5, the table size of 100, as we know, is 45. Now, more useful is a string. So if you want to build a hash for a string, for example, here you could add up all the different letters. So A plus B plus C, they've all got ASCII values or UTF-8 values. So that's 97, 98, and 99. That gives you 294. And then again, we use the same idea. We use the modulo of the table size to give us another number. So if it was 100, we'd give it 294 modulo 100. So here it is. So basically, you go through the string, you just add up every character in the string, and then you just use modulus on the table size. And so now you can store 100 strings in your table. And again, you're going to get some clashes, and that's for the other video. But this just shows you how you take a longer thing than the actual table and you create this integer or this place in the table. It's called a hash function, and that's what it's for. Okay, so let's try that out here. We can see the hash string of hello, comma, world, exclamation mark is 29. If we feed it a different string and say hello moon, then we get 18. So now you can see two different strings give different answers. Now, of course, you might want hash functions that are bigger than just, the table size of just like 100 entries, 200 entries, 1,000 entries. You can actually get hash numbers that are much, much bigger. And these are also good because they are a way of also kind of creating an ID for something. So you can use a polynomial rolling hash. Instead of just adding the characters, it repeatedly multiplies the current hash by a small prime and then adds the next character. So basically hash is equal to hash times 31, that's your prime, plus the current character. Okay, and then earlier characters are shifted along by multiplication before the later characters are added. So multiply then add, that's the point. This means that the character order matters. So ABC will give you a different result than CBA, which of course is good when you're dealing with hashes. And this function returns a full computed hash value, not a table index. So we've moved away from just simple tables now. Now we're going to get the full thing, which could be, let's say, a long integer. Okay, and then if you want to cut that down into a table size that's smaller than that, you can do that. But now we're kind of just concentrating on hash functions themselves and how they return this kind of number related to the input. And so here's that function. There's our prime number, and we basically say hash is equal to hash times by prime plus whatever the next character is. Go around in a loop, and when it's done, we return the hash, which is an unsigned integer. Okay, so let's try this algorithm. The polynomial rolling hash of hello world is now a much bigger number, 14987899909. Let's try an alternative string. And we can see, look, 37798879930. So quite a different number. Now, an interesting and well-known hash function is the DJB2 function. So it's a classic string hash function attributed to Daniel J. Bernstein. It starts with the seed of 5381, and for each character, it performs hash is equal to hash times 33 plus C. So in this implementation, hash times 33 is written as shift it left to the 5 plus hash. Why is that? Because shifting left by 5 multiplies by 32. So every time you shift it left, you multiply by 2. So times 2, times 4, times 8, times 16, times 32. And then you add the original hash that gives you 33. So here's the code. Here's the DJB2. So you start off with 5381. You go around your loop. And at the end of it, you return again an unsigned long. And if we now try DJB2, much, much longer number. Let's try a different string, and as you can see, a very different number. However, if we try hello world full stop rather than hello world exclamation mark, you can see the numbers are different, but they're actually quite similar. At the end there, it's 5531 rather than 5518. We'll talk more about that in a moment. Another popular one, again along the same kind of ideas, is the simple database manager hash. So for each character, it updates the current state by doing current character plus hash shifted to the left 6 times plus hash shifted to the left 16 times minus a hash. And what does that actually give you? That's actually C plus hash times 65599 because shifting it to the left 6 times is 64, shifting it to 16 times is 65536. You add those together at -1, you get 65599. Now the old hash is strongly mixed before the new hash is added. Again, character order matters. The large multiplier helps spread out things for similar strings. Different to DJB22, and therefore it produces a different distribution. And this is where, if you wanted to look into this, you can start investigating different hash functions. You can start mapping out how they respond to different types of strings. And of course, lots of people and lots of research on this. If you go onto the web, you can find many, many more hash functions than just the ones I've listed here. So here is the SDBM hash function. So again, we start by going round in the loop, getting to the end of the string, and there it is, C plus, and then the maths that I explained there. At the end, it returns this unsigned long again. Okay, let's try the simple database hash. So then again, hello world, and let's try that with hello world dot rather than exclamation. And we can see again the numbers there are very similar. They do alter at the end, 8693, 8706. So they are different, but they're not radically different. And this is all very well when you're dealing with data structures, but there are a type of hash function which are good for cryptography. So cryptographic hash functions. Now, so far we've been concentrating on speed. That's why we're doing things, shifting them to the left and all that kind of stuff, rather than just using normal multiplex. It's a fraction faster, which is good when you're dealing with high-speed databases. But cryptographic hashes have a different kind of idea. We need them for security. So in cryptography, secure hashes provide a unique fingerprint of data that's extremely difficult to reverse or forge, allowing a verification of integrity of passwords, digital signatures, blockchain transactions, while ensuring that even a tiny change in the input creates a different output, and that's called the avalanche effect. If you change one character, you get a completely different hash, not just a one character different hash. So what does that mean in terms of requirements? Well, it means that the cryptographic hash function needs to have a unique hash per input string, so it can be used to be representative of the input, which means that if I have a document and I say this is its fingerprint, this is its hash, and then I send it on to somebody else, they can't create another document that looks like it, has got the same hash, because they've been able to hack it, and create the same, but it's a different document, different values in it, different money, invoices, whatever it is I'm trying to transmit around. It needs to be one way, meaning that finding the input string that matches a given hash value is infeasible, assuming the input strings are equally likely. And the reason I put that there, of course, is that when you're dealing with things like passwords, the strings are not equally likely because there's a human involved, and they're going to put things like password 1234 as their password. And that's where you get this idea of a thing called rainbow tables, which is a way of pre-calculated hash values for all the common passwords, for example. And then you can look down a list of hashed passwords and you can say, oh look, I know what that is, that's password 1234, because it's this hash is a well-known hash. So it's one way only in the sense that the strings could be anything. So if you're actually sending an email or you're sending a document, then yes. But if it's passwords, if it's small data, then they tend to be easy to find. So MD5, Message Digest Algorithm 5, it produces a 128-bit hash value. MD5 was designed by Ronald Rivest, that's Rivest of the RSA fame, in 1991 to replace earlier functions MD4. But I put it in red there because it's no longer considered secure. You can get collisions and you can fake documents that will give you the same value as a different document. Then there's SHA1, the secure hash algorithm number 1, produces a 160-bit hash. It was designed by the NSA. It has been cryptographically broken, but under certain circumstances, so it's still widely used. However, people are moving away from it. Then there's SHA2, Secure Hash Algorithm 2, also developed by the NSA and currently considered to be secure. And there are many, many others. There's SHA3, Blake 3, Whirlpool, and these are just like 2 or 3. There are just so many, because this is actually an interesting field of mathematics and computer science. And so people have been working on this for decades to try to come up with the perfect cryptographic hash, the perfect data structure hash, and so on. Okay, so let's try it with an MD5, and as you can see, quite a long, and that's a hex string there. It's not just a normal integer that's been printed out. That's a hex number there, much longer. And now let's try it with only one character different. And as you can see, different to the other hashes we tried, we've got a completely different number now. So that's very important for cryptographic hashes. Now, the code for all those examples that I've been showing you are available in my GitHub repository. Okay, that's it, hash functions. As I said, there will be a follow-up video about hash tables, which use hash functions, but they are a separate thing. Love to hear any questions you have in the comments below so I can tackle those when I get to making that video. Okay, my name's Gary Sims. This is Gary Explains. I really hope you enjoyed this video. If you did, please do give it a thumbs up. If you enjoy this channel, then you've got a couple of options. Please do subscribe. And if you want to support the channel, do think about joining with one of the memberships. Okay, that's it. I'll see you in the next one.